This is slide number 11 and I am your presenter Asloob Mudassar. We have discussed earlier two types of objects, objects in transmission mode or the objects in the reflective or scattering mode. And we shall restrict ourselves to the transmission mode only. That is, we shall use only those objects through which the light will pass. Beam through a transmission object is well behaved in the sense that the beam can be defined mathematically, but this is not possible when it is scattered off an object. So therefore we shall restrict ourselves in Fourier optics to the objects which are in the transmission mode. Modeling of the incident beam. The incident beam that we shall be using may be spherically diverging wavefronts, spherically converging wavefronts, or the plane wavefronts. So we shall restrict ourselves to mainly to the use of the plane wavefronts most of the time, but sometimes we shall also be using the converging spherical wavefronts. And the convention that we shall use in Fourier optics is that the light will travel from the light will propagate from left to right, and similarly when we arrange our optical components in an optical system, we shall arrange them in the order from left to right, that the light will first propagate through the component at the left and then it will exit the optical system through the component at the right. Now, generation of a plane wave. As said earlier, that plane wavefronts will mostly be used in order to illuminate the objects in the transmission mode. So let's see that if you are using a helium neon laser beam, the beam that comes out is a plane wave, but the diameter of the beam is limited. That is very small diameter. We cannot use such a small diameter beam in order to illuminate objects of a bigger diameter. So what we do is that we need to expand the laser beam in such a way that it remain plane wave and at the same time the diameter is increased. For that one we can use a point source. That is, we can converge a laser beam at one point and from that one forming a point source, and then from that point source we shall generate plane waves of required diameter. So let's read the statement that a point source generates spherically diverging wavefronts. A biconvex lens in the path of a diverging beam separated by a distance equal to the focal length of the lens from the point source generates plane wavefronts. So quality of the plane beam depends on the quality of the biconvex lens used to generate it. If the lens has a very high quality, then of course the phase of the beam will also remain the same, will also be constant when it exits such a lens. Otherwise, if there are some distortions or if there are some dust particles on the lens, then of course the phase will vary on those points and the beam will not be perfectly a plane wave. The value of the phase on the wavefront is constant for a plane beam, and it is not important whatever its value, because when we measure the intensity of light, the phase value is disregarded. So this is the end of slide number 11.